peers talking about motos, especially this word about stacker moto. And if you're hearing stacker moto for the first time and wonder why are they talking like that? Why are they using these words that I don't understand? That's because stacker moto has got certain things that your peers are looking at. We all thought motor would just rotate, yeah, but there's more than that. If it's just rotating continuously, you have it for certain function. But if you want to rotate it to a certain angular position, then you should be looking at stacker motor. Then how to choose the correct stacker motor. Now stacker motor will come in step sizes. So what that means is that as it rotates, it will rotate in steps, very precise steps. And these steps are actually supplied by digital signal. So digital signal means that whatever number of bits that you have. So if you have higher number of bits, then you get a higher number of step size. So if you have to the power of 8, that means an 8-bit signal that's going to your stacker motor, so you can effectively control it precisely in 256 steps individually to exactly the position that you want. And if you want to, after that, yeah, I got that position and want it to stay in place with the load that's attached to it, then that's making use of another set of knowledge that we were talking about, hydraulics. Because hydraulics can make sure that after it turns, it stays in that position without you applying any brake. But if you want to use a stacker motor, move to that position and also want it to stay in that position, lock in that position, then you have, in any electric motor, have to have this brake mechanism, right? Because it cannot brake in place. You will have certain amount of withstanding torque, but if your load is going to be very heavy, then you would kind of like a wind jet. If it's very heavy, after you have supplied that amount of torque and still hold it in that position, it can only withstand this minimal amount of load, because the construction of a stacker motor is a brushless DC motor construction. Exactly. Brushless DC motor means that there's not much thing that's holding it except your magnetic forces. So if your magnetic force is strong, then you can hold it in place in that position stronger. Right. So stacker motors are so good in moving to a position of your desired choice by your digital input. So good that it does not require feedback at all. So if you were to use a brushless or a brushed DC motor to rotating and you say, I want to use that, I also want to be able to control its position of the shaft, then you need feedback. But your stacker motor, because it's in step sizes, so you actually do not require a control feedback system. Whatever digital signal that you send to it will just move into that position pretty well. So that angle is actually known to you by the number of bits that you send to that stacker motor. So there are actually 3 types of stacker motor construction. There's one that's permanent magnet. The other one is called variable reluctance. And then you have a third one that's a hybrid between those two. The permanent magnet for the brushless DC motor, you've already seen it before. It uses that permanent magnet in that core. For the variable reluctance stacker motor, what is the difference is that it's just like in your earlier lecture when we talked about the variable reluctance sensor. You'll find that in that core over here, instead of using a magnet for variable reluctance stacker motor, you will use soft iron. So it's not a magnet, it's just iron.
What does that mean? It means that what you need to do to energize all those coils over here, being a soft iron, it will just attract to that position sequentially. So you can see that the way it has been arranged, if you count the number of coils, it doesn't correspond to the number of soft iron extension that's coming out from the rotor. How many of that soft iron extension do you have? That's 4. How many coils do you get? 6. So it doesn't correspond. Why is that so? That's because these coils, they are energized in pairs, because you can see the wire over there is connected. They're energized in pairs to attract this extension of the soft iron core. So the soft iron core, they are not magnetic. So whenever there's a presence of these electromagnetic forces that's generated by the coil, then you would just attract to it. So if I want this position 1 to be attracted, position 1 to start rotating in a clockwise manner, what I need to do is actually to energize this and this coil. So instead of energizing this, I will energize this and this coil. So if I were to do that, then you see, I'm going to do a slow motion. You see it rotate. Right, let's do that slow motion. So originally it was this 1, 2, 3, and 4. And if I were to energize these 2, then 4 is going to be attracted, 2 is going to be attracted, and what you're going to get is this. Right? And the rest of it, they are actually not energized. And if I want 1 to continue to rotate, what I do next is to energize this and energize this. That will rotate. So it's that sequential energization that rotates my stepper motor. This is one construction of the stepper motor where it uses that rotor as the core, as the material is soft iron. That's so you could see that this A coil, B coil, and C coil, there's a certain on-off format that you can put in, and that is where is what we call the digitization signal that you can supply, either on or off those 3 coils, and correspondingly you get its position. So this figure and this table over here is not provided by Glasgow. We only have this range of words. So I thought it's easier to understand. You can work your way through how this rotor would rotate. So some students thought that, oh, I can see 1, 2, 3, 4 extension from the core. That means it can only have 1, 2, 3, 4 positions. So the step size of this is 90 degrees. It's not. Yeah. It's not the case. You can see that every step size is actually 30 degrees. Right? Because you have the number of coils that doesn't correspond to the number of extensions in the soft iron core. So because of that, it has this intermediate step size. It's not counting by 1, 2, 3 in that 1, 2, 3, 4. That's why 4 step size is not counted in that way. You got to look at the construction. So they are all together those number of step sizes. Now this is the construction of using a variable reluctance mechanism. There's another construction that's called a permanent magnet. So it's actually very similar to the construction of your variable reluctance, except that now this core over here, uses a permanent magnet.
So just now it was a soft iron core, just a piece of metal over there. So obviously if you energize the core, it can attract the metal. But this construction over here uses magnet. And what we're gonna do to exploit is that we're gonna have, again, the electromagnetic forces creating a north pole over here. And if that core here has a south pole, then you can see that it can attract each other a lot more stronger. Instead of having a electromagnet and then a soft iron core. I changed this soft iron core into a magnet. Now that attraction force is going to be a lot more larger. Why is this desirable? That's because if I have magnet and magnet, those two magnetic forces could move your core a lot more, giving it a lot more higher amount of torque. If it's soft iron core, and that amount of torque is actually less. So by sequentially activating the cores, you can see that core can move through that sequential step sizes and providing at the same time higher amount of torque because it's magnetic and magnetic attraction. So this one such example. The next step of that is to have, actually I prefer this picture to come in after this step. So you can see your north and south pole for your permanent magnet is always going to be the same. So in order for this south pole to start rotating toward the clockwise direction, what I'm going to do is to create this one as north and that one over here as north as well, shown in this figure over here. So in that case, your south pole will move kind of like a 45 degrees in between. And after that, I'll de-energize this north pole at the top, and then maintaining my north pole at this, the one on the right. So you can see that sequentially, this core is going to rotate continuously. So those are the things that can be done to move that magnetic rotor, and it's going to give us the step sizes. So in this case, you have by increasing the number of coil pairs, you can have 15, 30, or 45 degree step angles. But in a lot of cases, your stepper motor will offer you higher resolution. In fact, I think a lot of stepper motors would give you more than an 8-bit kind of signal. So you have a lot of step sizes at a smaller angle, and that angle will be very precise. So if you want to buy a stepper motor, try to find out if that core, is it soft core or a magnetic core. Magnetic core will give you a larger amount of torque. Now, let me play a video. This video over here. It may be a little bit noisy. Hear the sound. Sounds like what does it sound like? That's starting part, and the rest are the same. That's starting part. Let's listen again. Yeah, sounds like. Yeah. That is your MRT. MRT sound. So why is it that when you see on an MRT you get to hear this whining sound that's increasing that way? Is the action of PMAG that's going on. PMAG, permanent magnet AC motor, very strong. Why is it that strong? Let's have a look at the construction. So this figure over here It's something I added on. I think there's a T missing. Permanent. Yeah, permanent. Oh, it's still here. Permanent magnet.
Now you can have your permanent magnet that's designed just like your brushless DC motor, but why is it considered an AC? That's because the signal that we're sending inside the various coils are AC current signal. Now AC current signal, what does that mean? So AC, it looks like that, the wave, and when it goes up to the positive, the current will increase up to a maximum, and then it's going to drop, and then it's going to be in the opposite direction because minus, and it's going to increase to the maximum opposite current direction. And what that means to us in our coil, those coils over there, the positive and the negative current, it just means that it's changing that electromagnetic force, electromagnetism to a north or south pole. So when it's going up, maybe that's your north, coming down, that's your south. So it's alternating the polarity of your core, of your coil, right? So that maybe that one in the blue circle, maybe we start by having energizing it, so it will become more and more north, more and more powerful north, and then that strength would drop, the north would drop, and then it would turn weak south, and then strong south, and then weak south, and then turn to north again in that alternating current cycle. But how about for that construction?
There are two types of construction. One is using that core that's north-south in that way. But most of the time that you can find the permanent magnet, they try to exploit every bit of it. Yeah. These are spaces that are wasted. So they have this circular magnet, permanent magnet, where you have part of it that has been made to be a north, and then south. It is actually possible to have a magnet that is magnetized in that way. So if you have that rotor in this construction or in this construction, no problem as well. This one will give you a larger amount of force, this one will be lesser. But let's take a look at this because it's easier to understand. There are only two of it, north and south. Let's have a look at that. So I have this current coils that's going in. So that one that's in yellow will go through in that way. And then exit. And then we supply this alternating current. Right? So that alternating current, it will energize this, energize this, energize this, and energize this. Right? And I just want you to focus on the part when we energize it to the maximum south pole. Say for example this one becomes a south. So what's going to happen is that this north magnet is going to not south, north. Yeah. So what's going to happen is that it's going to repel that, and as it repels, you could see that your red color that's next to it is actually a south. So one side of it is becoming a north, the other side is south. You could see that there's a huge attraction for this rotor to want to rotate clockwise. Yeah. And your green one over there is kind of like in between here. In between this, if I draw that neutral line, it's also going to be slightly south. So kind of like smaller S. This is a larger S. Yeah. So you can see that the rotor really want to flip to the next angle very strongly. Permanent magnet inside, and a very favorable condition for it want to rotate. So because of this favorable sequential oscillation of your current through these three coils, what's going to happen is that it provides it with a tremendous amount of torque. And this tremendous amount of torque is good to start up a heavy vehicle such as a truck. So that's why PMAC motors are used in trains, because of this tremendous amount of torque. This everything put it in already. You have the core that's made of magnet so as to really provide a powerful repelling, and then the other side attracting so you will move. So the amount of out of phase that you could see is 120 degrees. So this current here, they are all 120 degrees out of phase. How do I see that? This peak over here, maybe if I zoom in, right? This one over here, 120, 120, and 120 degrees. So maybe this 0, this 120, 240, and this part 360. So this tip now comes over here, so it's 120 degrees out of phase, and then that is 240, so another 120 degrees out of phase. So you can see that these three AC signals or the AC current, they are 120 degrees out of phase. Now the speed of a rotation of this magnetic field is what we term as a synchronous speed. So sometimes you get it here for PMAC, they don't just talk about speed, they talk about synchronous speed. And that's because it has to be synchronized here. So the synchronous speed. And the rotor will rotate at a rate of 1 to 3% less than that speed. Because it's not a physical gearing system that will rotate the shaft, but using magnetic forces to repel and attract. So although your activation of your coil is at certain speed, but eventually when your rotor starts to rotate at that speed, it's actually 1 to 3% lesser than your activation of your coil speed. So it's because it's using magnet, it's not a gear system that will be moving that shaft in an absolute sense. So this few slides over here explains that. A lot of what I spoke about is already in there. This one relates to the 1 to 3% of full speed or the full frequency, the synchronous rotation frequency. And if you put those three AC signals together, you get this waveform. So you can see that this peak is 120 out of the other peak is 120 degrees out of the other peak. Let's do a comparison between the brushed DC motor and the brushless DC motor and the AC motor. There are three major things that are different between the different motors. The first one, speed control. The DC motor, as we have seen, is varied by changing the current that's going through the system. And we know that increasing the current, the speed will increase. That one we have seen before. The speed of the AC motor, conversely, is a function of the frequency of that synchronous activation of that coil. So that's where it's different, right? The speed for the DC motor is controlled by current, but for this one is on the synchronous activation of the coil. The second thing that's different between the brushed and the brushless DC motor, AC and stepper motor, is that for the brushed motor, the lifespan is actually quite limited because of that brush and the commutator. So there's a limit to its lifetime. Compared to the brushless, we can see that it's giving us a longer shelf life. It's able to last longer because all your stepper motors, they're actually in a construction similar to a brushless DC motor. Even when you look at your PMAC, it's also a brushless configuration. The third difference is what I was talking about, the dissipation of the heat. And in fact, later we'll have a mathematical treatment to the amount of heat that's generated. The heat that's generated will cause an increase in the temperature of your coil. And how will that coil change its resistance or its torque constant under the increasing heat that's being generated? So later on we'll have a look at that. But what it's trying to say is that it talks about the dissipation of the heat, where I was talking the difference between your brushed and your brushless DC motor is that for your brush, the heat is trapped inside, whereas for your brushless, because the coil is on the outside, heat is able to dissipate out. So that's the other major difference. Now, some people actually argue, okay, you have a lot of heat that's generated, right, for your brush DC motor, but I really love a brush DC motor. How about if I were to increase the thickness of the wire? Because if you were to increase the thickness of the wire that's coiling inside the brush DC motor, it can accommodate higher current for a thicker wire that's coiled around. That's true, but isn't thicker wire means heavier motor more expensive, because thicker wire is more expensive? So there's that balance that we have to make. It's not always if you want higher amount of power, you go for a thicker wire that's coiled inside. So this part also talks about for your AC motor, which is a brushless DC motor design. You can afford higher current without damaging the motor, and that's why they are actually more powerful. Your AC motor is a lot more powerful. We don't have a three-phase AC supply. Some of the motors that you want to buy, please know that you're not buying a three-phase motor. If you buy a three-phase motor, you will not run in your lab. Okay? And three-phase motors are not cheap. So overheating is bad because you get short circuit, and not only it damages your winding, but for your bearing, it also will affect it. And if the bearing starts to get heated up, you could potentially get jamming on your rotor shaft. And under high heating, your permanent magnet will also degrade. So your permanent magnet, maybe you've heard before. Actually, I heard before when I was in primary school. Remember, they give you this iron nail, and then you kind of use a permanent magnet, and then strike it, and then it turns it into a permanent magnet. And at that time, did you ask your science teacher, how can I remove that magnet now? Yeah, you heat it, yeah. So that's one way. Is there another way? Did you ask that question? Another way is to put this into an oven. If you were to heat it up, under heat, your magnetism would lose its effect as well. So that's what's going to happen in your motor. If it's under constant high heat, your permanent magnet would lose its effectiveness permanently. Yeah. So that's why we need to cool down the motor. So this heat that's generated in the motor is nonlinear. Later on we'll see some mathematics behind it. It's coming from the winding, your magnetic flux will degrade. It's just repeating. It's just repeating. Okay, let's have a look at these few sets of equations. And I'm going to sketch separately so that you are able to see, instead of just looking at this equation, not knowing where it comes from. So I'll just do a separate sketch. What I need you to know is this part over here. This P stands for power. Power that's generated by the heat. Your MDE peers, they would tell you heat generated, we use a letter Q. Over here, this note uses P to say that there's a power that's generated due to the heat, the heating power. But mechanical engineers don't use this kind of words. It's okay, we're mechatronics. So power is equal to I squared R, right? That's the equation. I squared R, that's your power. So let's have a look, because your I is equal to T over K, because T is equal to K T I, if you remember. So I is equal to T over KT. That's why we replace this I squared into a T squared over KT squared. Okay. Now what I want is to show you about this thing, because this thing relates to your electrical resistance of your winding as the temperature would increase. So if I just sketch that increase in temperature with the axis of resistance, so this resistance is in terms of ohms, the resistance that's found inside the coil of wire. Have that with a treatment against temperature. What is that relationship? You'll find that we'll start with an original temperature. I'm not sure what original temperature it is, but in our room temperature, we call it the reference temperature. This is just an extrapolation. So under room temperature, which I call reference temperature, you have a certain amount of resistance that you can find in your motor. And as you were to increase your temperature to what I call the winding temperature, so as you energize your motor, your winding, that is the winding of the wire, is going to have an increase in the temperature in this way. And I call this RT. You will have a higher amount of resistance, where RT is resistance at a temperature that I call T. So at a higher temperature, you will have a higher amount of resistance. So just this line over here, this is an extrapolated line, not necessarily crossing zero. T winding, I'm going to use the symbol TW subsequently to represent T winding. So if I were to find out what's the gradient of this, that will be RT over R ref equal to RT, is RT, that's TW minus T naught, right? TW over here minus T naught, divided by T ref minus T naught, T ref minus T naught. Right? So if I were to solve this, RT over R ref, taking out the common factor, 1 over T ref minus T naught, bracket, and whatever that's left inside TW minus T naught, TW minus T naught, I'm going to fill in something in between, minus T ref plus T ref, right? So I'm not changing anything. Why do I do it in this way? There's some reasons for that. Now my RT over R ref can be simplified by taking this part and that part in that way. So what I'm going to have is TW minus T-rad over T-rad minus T naught plus 1. Yeah. And I'm going to simplify this further into 1 plus TW minus T-rad and multiply it by alpha, where alpha is 1 over T-rad minus T naught. And there's actually a special name to alpha. Alpha is called our temperature coefficient of the winding material. The temperature coefficient of the winding material. So the temperature coefficient of the winding material is a characteristic of that material that's coiling your rotor. So you could see that if you were to increase your winding temperature, that means you put in a lot of current to that rotor coil. What's going to happen is that that rotor coil correspondingly you will have an increase in that resistance. But what does that mean to us? If the motor is getting hot, it means its resistance will increase. What does that mean to you? What will become of the performance of that motor speed when the resistance increases? Right. It will affect your performance because now with more resistance, how are you going to drive your motor? You need to supply more power. So this is not good. More power means that you'll heat up more. Right? So that's that saturated limit that you can do in order to energize your motor to run even harder, because that resistance will increase as you drive it harder. There's another part that talks about the torque constant KT. So I'll do a sketch. It's in your other slide. Yeah. I'll do a sketch for that. The torque constant that represents the magnetic field of the motor, and that magnetic field will vary as the temperature increases, and hence affects your torque constant KT. So I'll sketch that. This axis will be torque constant, and that axis again is temperature. So we want to find out how temperature is affecting our torque constant. So again, we're going to have this as our reference temperature. So reference temperature can be room temperature, and we have the torque constant as my reference torque constant. And as we increase the temperature, respectively, your torque constant is going to increase. So I call this part as my temperature, but instead of the winding, it's for the magnet, because it is your magnet that will affect your torque constant. So correspondingly, this KT over here, capital letter KT, will be your torque constant. So I'm going to use the same ratio, that is KT divided by Krad equal to T magnet minus T naught divided by Trad minus T naught. And just doing a little bit of simplification, KT is equal to Krad yeah, doing the same kind of simplification, but I'm not going to solve that. Eventually you get 1 plus bracket T magnet minus T rep, and multiply by this beta over here, where beta is called our decay of magnetic flux. So what that means is that as you were to have more decay of your magnetic flux that's governed by B, that will respectively affect your torque constant. The units for alpha and beta is Kelvin to the power minus 1. So the units for this, Kelvin to the power minus 1 for alpha and beta. A little bit of note, your T winding is actually equal to your T motor. So I think I'll be uploading a tutorial where your T is given to you as the temperature of a motor, because your motor construction is the same as the winding construction where heat is experienced. So sometimes these two are used interchangeably. So that's because for brushless motor, it is made up of winding at its extremities. That means in the outer shell. Extremity is in the outside of your motor. So the brushless DC motor, you have that winding at the outer shell. We call it extremities. So that equation that we saw just now, the heat generated by the motor, I call it pH, and that one has a unit of watts. So pH is equal to I squared R T. So you have seen before, it relates to the torque and the torque constant in that way. So this is also in units of watts. But this is a heat generated by the motor. The total heat generated, there's one more component of that. There's pH plus the friction. And friction could come in various different forms. For your brushless DC motor, it's going to come from the shaft bearing. So usually this one is coming from, a lot of it is coming from the bearing, giving that increase in the heat that's generated. So the equation for that is T motor minus T rad divided by R thermal. Now how this came about, because it's actually a thermal resistance. This is actually more for MDE students, but I'll just cover a little. Temperature of the motor to the temperature of your ambient. You will face a thermal resistance that I call R thermal. So heat is transferring out in that way. That's your pH plus T friction. It's kind of like a thermal circuitry where heat is transferring from your motor that gets heated up to the ambient temperature. And in between, there is a thermal resistance. Now this thermal resistance would accommodate the convection. There's a convection thermal resistance that's coming in because there's a layer of air in between. So I can re-express this expression as T motor equal to PH plus P friction. R thermal plus G rad. Now the units for R thermal is actually degrees Celsius per watt or Kelvin per watt. Either one, they are interchangeable. Now the next set of table over there outlines the various advantages or disadvantages of brushed DC motor, stepper motor, brushless DC motor, and the PMAG. There was a year that this table was asked as one of the questions, and it's just repeating this table and put it in, you get it through one. Yeah. So that table, this table over here. There are some highlights. You can see that the stepper motor, even though it gives you a sense of positional control, the maximum speed is limited. For your brushless stepper PMAG, you can see all the maintenance is low. The brush is because of the brushes inside. And the torque ripple refers to your amount of torque that's applied to it. Is it a constant or is it jittery? So for a stepper motor, you'll find that it's more jittery because of the step size. So that's one of the disadvantages of the stepper motor. So that's why that's high. Shaft position encoder, is it needed? So you can see that none is needed over here. For PMAG, if you want high resolution, your shaft encoder will be needed. And that's actually your Hall effect sensor, and that actually will also increase the cost. Okay, that's all I have. Have a wonderful public holiday. Happy Chinese New Year. Please collect